Good day, my team's topic is casting, foundry practice, and it will cover furnace types and pouring practices.
There are 3 members in the group. First, there is Hafiz Low. Second, there's Elijah Wulija. And the third one is me, Mikol Chang.
Next, casting is one of the oldest and most versatile manufacturing processes. It involves pouring molten metal into a mold, allowing it to solidify, and then removing the solidified part. And that leaves us with the final product. Foundry practice refers to the industrial procedures, tools, materials, and quality controls used to produce castings efficiently and reliably. Next is the basic principles of casting. There are 7. The first 3 are pattern making, mold making, and melting and pouring. As for pattern making, it is done by getting a replica of the final component used to form the mold cavity. The materials here is usually steel or metal as seen in the picture. Next is mold making. It is done by using sand, metal, or ceramic, and then it is prepared as a mold for the materials. And next is melting and pouring. The mixture of sand, metal, or ceramic is heated in a metal to its molten state and then poured into the mold. Next 3 are solidification, shakeout, and cleaning and fettling. For solidification is very straightforward. It's the process of allowing the molten metal to cool and solidify inside the cavity of the mold. As for shakeout, it's also very straightforward. It's to just shake the mold until the material comes out. And then lastly, cleaning and fettling. It is done to remove excess metrical, gates, risers, and surface impurities for the final product to look more polished. Lastly is inspection. It is also very straightforward. It's just the process of checking the final casting for dimensional accuracy and defects. So there are a few important elements of foundry practices. The first is patterns. Patterns are made from wood, metal, or plastic and can be found in single piece, split pattern, match plate, cope and drag, and shell pattern types. Patterns require allowances for shrinkage, draft, machining, and distortion. Next is molding materials. Molding materials include green sand, which is a mixture of clay, water, and silica, and then dry sand, CO2 sand, shell mounts, and investment molds. This is to ensure strength, permeability, which is the ability to let fluids or gases pass through it, refractoriness, the ability to withstand high temperatures and loads without deforming and melting, collapsibility, which is the ability of a mold material to easily break down and disintegrate after the casting has been solidified, and lastly is flowability, which is the ability of a material to flow or move easily. The last element is cores. Cores are used to form hollow or intricate internal cavities and are made from sand bonded with resin or oil. And these are common patterns used in foundry practices.
Now we'll talk about the types of furnace in foundry practices. So there are 3 furnaces. First, cupola. Second, induction. Third, electric arc. Fourth is crucible. And the last one is reverberatory furnace. It is important to choose the right furnace as each furnace has their own functions. For example, if you want to cast an alloy, cupolas are most exclusively used for cast irons. Meanwhile, crucible furnaces are ideal for non-ferrous or non-iron metals. Next, melting temperature and capacity requirements. A small foundry has low capacity needs. Meanwhile, a big, massive steel foundry requires an immense rates of an electric arc furnace as it is big and also it can have retain really high heat. Third, if you don't pick the right furnace, you lose a lot of money in terms of investment and also operation. Next is also quality and composition control needs. For critical components, an induction furnace allows for precise chemistry control as it is in a controlled environment which only the metal is in it with the heating element. Lastly, environmental and efficiency considerations. As modern foundries have moved toward electric furnaces, induction or electric arc furnaces for cleaner operation and higher efficiency as they retain heat and also not use a lot of energy. You can see in the diagram, it is a tall vertical shaft where layers of metal, coke, fuel, and also limestone are charged from the top. It works by air being blasted in and burning the coke to create intense heat. It's a robust and high capacity method, but it's primarily limited to iron and produces significant emissions carbon emissions. It is used for usually melting large quantities of cast iron. It is a traditional choice for foundry practice to pick cupola. Secondly, I will explain about the induction furnace. It is perhaps the most versatile and controlled method when it comes to melting metal. There is an electromagnetic coil that surrounds the metal, inducing electrical currents within the metal itself, causing it to heat up from the inside out. This method is clean, fast, and provides exceptional control over temperature and also chemistry, making it a top choice for quality ferrous and non-ferrous castings, as it is in a controlled environment, as I've said before. Third, we have the electric arc furnace, or known as EAF. When it comes to melting steel, especially from the scraps, EAF dominates the industry. It uses power electric arcs struck between graphite electrodes and the metal to generate immense heat, as we've talked about before, like induction furnace. The EAF is known for its massive capacity, and it is a cornerstone for modern recycling, as it is very efficient when it comes to melting scrap metals. We have the crucible furnace. It is typically used for small scale operations like a jobbing foundry or a research and development lab. The crucible furnace is ideal. So we've already done experiments before when we were in high school, whereby we used the crucible to actually separate aluminium and the oxide, or include oxide into the aluminium. The metal is placed in a ceramic graphite pot, the crucible, which is heated from the outside. This indirected method is simple, low cost, and excellent for preventing contamination, making it perfect for small batches of non-ferrous alloys. Lastly, we have the reverberatory furnace. It is typically used for non-ferrous metals like aluminium and copper. A reverberatory furnace usually burns or heat the roof and the walls to radiant heat, or reverberates down to the metal and melt it from the heat created outside. This allows for large volume melting, but also can lead to higher metal oxidation because it burns from the outside in, which allows for air to trap inside. So hence oxidation. So now that we've talked about the furnaces, we will talk about pouring practices, or the processes when it comes to pouring molten metal after it has been burned inside the furnace. So the process starts with tapping of the furnace. A sealed hole at the bottom of the furnace is open, allowing the molten metal to come out or flow out of the furnace. Secondly, we have transfer to a ladle. So a ladle is used to actually, third part, pour the molten metal into a mold. It is important to use a ladle as it is controlled by the person, and it is to safely transport metal from the furnace to the pouring station without spillage or damaging anyone. The pouring practice, there are two really important or critical factors that everyone should know. Firstly is the temperature, and second is the pouring rate. So for the temperature, when it comes to pouring metal, when it's too hot, the metal is too fluid and it will ruin the casting, especially sand castings, as once sand gets too hot, it becomes glass, and then it will stick on the metal cast itself, which creates a rough surface and not a pretty finishing. But if the metal is too cold, the metal is thick and sluggish, therefore it will freeze before it is casted, and it will not become a perfect cast, and it will not have the imprints of the mold. Second, pouring rate. If you pour too slow, the metal will get cold faster, and hence it will be the same as what happened if the temperature is too cold. Misruns can happen, and unfilled cavities will occur. Secondly, if it's too fast, splashing and rushing occurs, which will ruin the sand casting, as the force or the velocity of the fluid molten metal is too fast and it will just ruin the sand casting. So here we are going to talk about the gating system. It is to show the process of a casting from the pouring itself to the casting. So firstly, we will talk about the main components and its functions. The pouring basin, it is a funnel that keeps the metal flow smoothly. And then we have the runner, which is a horizontal tunnel that carries the metal from the bottom of the sprue. A sprue is a vertical pipe that stops air from being sucked down with the metal and create cavities or gas holes, gas bubbles. And fourth, we have the gates, which is the final nozzle or inlet for the metal to enter the mold cavity slowly. As you can see from the diagram that we did not talk about the riser, it is a crucial and important part of the gate system. So the riser is an important tool to prevent shrinkage and also cavities forming inside the metal cast. So what is it? It's an extra lump of metal that is added to the casting as a sacrificial reservoir. Why? As I've said, it is to prevent shrinkage, and also cavities. Third, it is designed to be the last part to solidify. While cooling, liquid metal flows from the riser into the casting itself and fills in the gap. So because it is the last part to solidify, it will ensure that whatever is inside the cast will have enough molten metal to become hardened. The key rule of riser or the whole part is casting must solidify first before the riser, as if it does not solidify before the riser, then there's no point of the riser. This part is actually called directional solidification.
Okay, so for casting defect, the common defect and causes is first for the defect is porosity gas entrapment, and the causes is poor permeability. Second is shrinkage cavity, and the causes is inadequate risers. Third is misrun. The causes is insufficient fluidity, cold shut, two metal streams not fusing together, sand inclusion, loose sand, improper mold, and lastly hot tears, thermal stresses during cooling. Inspection method also includes visual, X-ray, ultrasonic, and dye penetrate testing. And next is the advantages of casting. So there are four advantages. First is it can produce complex shape easily. Second is suitable for large and heavy parts. Third is work for almost all metal. And fourth is it is very cost effective for low to medium production. Okay, next for limitations. Surface finish can be rough, especially for sun casting. Dimensional accuracy might be lower than machining or forging. Defects are also more likely compared to processes. Example for defect is porosity. Okay, so in summary, casting and foundry practice forms the basis of metal manufacturing. With proper control of pattern, mold, melting, pouring, solidification, high quality cast part can be produced for industries like automotive, aerospace, machinery, and construction.